Shall we learn about problems related to quantum numbers? Now let us look at the problem 2.17. What is the total number of orbitals associated with the principal quantum number n equal to 3? So you are given n equal to 3. It indicates third shell. Okay, you are asked to calculate the total number of orbitals present in the third shell. When you learnt about principal quantum number, you should have come across this formula. The number of orbitals in a shell is equal to n square. When n equal to 3, you have 3 square, which is 9 orbitals. So there are 9 orbitals in total in the third shell. This is the answer. There is yet another method of solving this problem. Okay, now you can see how we can do that. Okay, when n equal to 3, we know that it can have 3 possible values of L. So what are they? 0, 1 and 2. Okay, I've written everything in the tabular form. Okay, when n is 3, L can have 3 values. What are they? 0, 1 and 2. Okay, the subshell notation corresponding to these n and L values are 3s, 3p and 3d. We know very well that if L is 0, it stands for S subshell. If L is 1, it means P subshell. And if L is 2, it means D subshell. Since these 3 subshells are inside the third shell, you write the number 3 near each SPD and SPD notation. Okay, so you get 3S, 3P, 3D. Now, the values of ML. If the value of L is 0, the value of ML would be 0. If the value of L is 1, then you have 3 values for ML. What are they? -1, 0 and +1. If the value of L is 2, then you have 5 possible values for ML. What are they? -2, -1, 0, +1 and +2. So these represent the number of orbitals that is possible in 3s, 3p and 3d. Okay, when the value of ML is 0, it means there can be 1 orbital. When there are 3 values, it means there are 3 orbitals. When there are 5 values, it means there are 5 3D orbitals. So, what is your answer? Your answer will be the sum of these number of orbitals of S, P and D. Okay, so when you add 1 with 3 and 5, you get 9 orbitals in total. So you can follow any of these methods in solving this problem. Okay, whichever method is convenient to you, you can apply that method and work out this problem. Let's solve problem 2.18. Using SPDF notations, describe the orbital with the following quantum numbers. Here in this question, you are given 4 sets of quantum numbers and you are asked to describe the orbital specified by each of these sets using SPDF notations. Let's try to solve this. Okay, I have tried to solve this in tabular form. Okay, I have written the question numbers in the row, first row. Okay, now let's solve the first case A. Here n equal to 2 and L equal to 1. N equal to 2 indicates second shell, and if L is 1, it means it indicates P subshell. Okay, so this is a 2P subshell and the orbital corresponding to it is 2P orbital. Okay, this is the orbital. 2P is the orbital described by these quantum numbers n equal to 2 and L equal to 1. Okay, coming to the second case. Here n equal to 4. This indicates fourth shell and L equal to 0. This indicates S subshell. Okay, so 0 stands for S subshell. Since S subshell is inside the fourth shell, since n is equal to 4, okay, this describes a 4s subshell. And the corresponding orbital is given by 4s orbital. Okay, this is the solution for the second case. Coming to the third case, C. Here n is L, n is 5 and L is 3. N equal to 5 stands for fifth shell, and if the value of L is 3, it indicates F subshell. So what is the subshell we are dealing with? It is 5f subshell, and the orbital corresponding to this subshell is 5f orbital. This is the orbital described by n equal to 5 and L equal to 3. Now coming to the last case D, here n equal to 3 and L equal to 2. Here, since n equal to 3, it indicates third shell. If the value of L is 2, it indicates D subshell. So what is the subshell? It is 3D subshell. The orbital corresponding to 3D subshell is 3D orbital. So this is the solution. Okay, this is the orbital indicated by n equal to 3 and L equal to 2 quantum numbers. Children, I want you all to do this exercise problem 2.29 as your homework. Using SPDF notations, describe the orbital with the following quantum numbers. As usual, you are given 4 sets of quantum numbers, and using these quantum numbers, each set of quantum numbers describe the orbital as we did in the previous problem. Let's do the exercise problem 2.24. What is the lowest value of n that allows g orbitals to exist? Okay, you are asked to find out the shell. Okay, you are asked to find out the shell in which you come across g orbitals for the first time. Let's see how to solve this. G orbitals exist in G subshells, and what would be the value of L corresponding to G subshell? It would be 4. Look at the tabular column. When you write SPDFG and if you write the corresponding values of L, you find that the G subshell has the value of L as 4. And if you try to write the corresponding values of N, okay, you find that you can find G subshells in the 5th shell. So, therefore, for a value of L is 4, the value of N is 5. This means that only in the 5th shell you would come across G orbitals. Let's deal with exercise problem 2.25. An electron is in one of the 3D orbitals. Give the possible values of N, L and Ml for this electron. So, what is the information given to us? It is told that an electron is present in one of the 5 3D orbitals. Now, we are asked to write the corresponding values of N, L and Ml. I have solved this problem in the tabular format. Okay, orbital. What is the orbital given to it? Given to us, it is 3D orbital. Okay, 3D. Here, 3 indicates the value of N. Okay, the value of N is 3. This means the electron is in the 3rd shell. And what is the subshell notation provided to us? It is D. It indicates the D subshell. So the electron is in 3D subshell. And the value of L corresponding to the subshell notation D is 2. And from this, we calculate the values of ML. And when we substitute this value of L into L plus 1, you get 5 values. What are they? -2, -1, 0, +1 and +2. Okay, these many orientations are possible for the electron present in the 3D orbital. Here's problem, exercise problem 2.28. Here there are 3 questions. The first question is, an atomic orbital has n equal to 3. What are the possible values of L and Ml? Let's try to solve this first. Okay, I worked out this in the tabular form. Now we know the value of n is 3. So when n is 3, L can have 3 possible values. And what are they? 0, 1 and 2. This is written in the second row. Now when the value of L is 0, Ml can have only one possible value. What is that? It is 0. And that is written in the last row. And when the value of L is 1, it can have only 3 possible values. What are they? -1, 0 and +1. When the value of L is 2, it can have only 5 possible values, and they are -2, -1, 0, +1 and +2. So this is the solution for the first question. Coming to the second question, list the quantum numbers of electrons for 3D orbital. For 3D orbital, we know that the value of L, that is what we are asked, isn't it? The value of L for a 3D orbital would be 2. Why? When you have D orbital, the value of L corresponding to D is 2. Okay, so L is equal to 2. Now, ML can have 5 possible values. If the value of L is 2, then ML can have 5 possible values. See how I have worked out the values of ML when the value of L is 2 in the previous solution. Okay, look at the tabular form. Okay, so ML can have 5 values. What are they? -2, -1, 0, +1 and +2. And this is the solution for the second question. Now coming to the third question, which of the following orbitals are possible? They have given 4 different orbitals, 1p, 2s, 2p, 3f. We are asked to find out the allowed orbitals among these. Now let's solve this. Take the case of 1p orbital. Is this possible? 1 of 1p indicates n is equal to 1, which means first shell. When n is equal to 1, L can have only one possible value. And what is that possible value? L can only be 0. If L is 0, then it should correspond to s orbital. But look, you are given p. If you want to have p, then the value should have been n. But it is not possible because when n is equal to 1, the value of L can only be 0. And 0 stands for s orbital. So you cannot have 1p orbital. 1p is not possible. Now coming to the second orbital, 2s. Is this possible? Yes. Why? Here the value of n is 2. Okay. When n is 2, L can have 2 possible values. What are they? 0 and 1. Okay. For s, the value of L has to be 0. And this is satisfied. So 2s is possible. Now coming to the third orbital given, 2p. Is this possible? Of course it is possible. Why? Here the value of n is 2. Okay, when value of n is 2, L can have 2 values. What are they? 0 and 1. Okay, and in the given orbital, what is the orbital specified in the case given to us? It is p. When you need a p orbital, the value of L has to be 1. And is it satisfied for n is equal to 2? Yes. N can have 2 possible values, 0 and 1. So the orbital 2p is possible. It is an allowed orbital. Now coming to the 3f orbital. We should see whether it is possible or not. Here the value of n is 3. When value of n is 3, the values of L can be 0, 1 and 2. So if you write the corresponding subshell notations of L, that is for 0, 1 and 2, you can write the subshell notation as S, P and D. Okay. You cannot extend this to f orbital. So 3f is not possible for n is equal to 3. Exercise problem 2.30. Explain giving reasons which of the following sets of quantum numbers are not possible. Here you are given 6 sets of quantum numbers, and what are you asked? You are asked to find out which set of quantum numbers are not possible, citing suitable reasons. Okay, let's solve this. First of all, I have tabulated the values of n, L and ml. Okay, so this is done as usual. Okay, when the value of n is 1, L can have 0 value and ml also can have only 0. When n is 2, L can have 0 and 1 values, and when L is 0, the value of ml would be 0. If the value of L is 1, then ml can have -1, 0 and +1. When n is 3, the possible values of L are 0, 1 and 2. When the value of L is 0, then the value of ml would be 0 only. When the value of L is 1, the value of ml can be -1, 0 and +1. When the value of L is 2, it can have 5 possible values. What are they? -2, -1, 0, +1 and +2. Now what we are going to do is, we are going to compare each set of quantum numbers with the possible quantum numbers for each value of n. Okay. Now don't give much importance on the values of ms. The values of ms can be plus half or minus half. And if you find any other number other than half, then that set of quantum numbers becomes impossible. Okay, only if you come across that situation, the whole set of quantum number would become unallowed. Now, when you have plus half and minus half, you need not bother about that. Okay, so let's start solving each set. Consider the first case. Here n is equal to 0, L equal to 0, ML equal to 0 and MS is equal to plus half. Now look at the value of n. Value of n indicates the shell. Okay, in any atom you have shells, first shell, second shell, third shell and so on. Do you have a zero shell? No. So this set of quantum numbers stands cancelled. It's not allowed. It is not possible to have this set of quantum numbers. Now coming to the second one, B. Here n is equal to 1, L equal to 0, ML equal to 0, MS equal to minus half. Let's concentrate on the first three quantum numbers n, L and ML here. N equal to 1. It indicates the first shell. As you know, when n is equal to 1, L can have only one value. What is that? 0. Okay, so it means S orbital. Okay, so when L is 0, ML can have only one value which is 0. So this means that the orbital specified has only one orientation in space. So this indicates, these three quantum numbers indicate the S orbital, 1s orbital. Okay, so this set of quantum numbers is allowed. Coming to this third case, C. N is equal to 1, L equal to 1, ML equal to 0, MS equal to plus half. Consider the first three quantum numbers here. N equal to 1 indicates the first shell. L equal to 1. Can you have L equal to 1 when N is equal to 1? No. The value of L is equal to 0 when N is equal to 1. So you cannot have this set of quantum numbers. It is not possible. Okay, now coming to the fourth case. N is equal to 2, L is equal to 1, ML equal to 0, MS is minus half. Okay, is it possible? See, N equal to 2 indicates second shell. Okay, now we know when N is 2, L can have two possible values, 0 or 1. Okay, and here the number given is L is equal to 1. You can have this value, it is possible. Okay, so here 1 stands for P. Okay, P orbital. Therefore, the fourth set of quantum numbers is possible. Okay, ML value is also possible. Why? When the value of L is 1, ML can have three possible values, minus 1, 0 and plus 1. So 0 is one among these three values. So the fourth set of quantum numbers is possible and this indicates 2p orbital. Children, I want you to have E and F sets of quantum numbers as your homework. When you come for the next class, do this homework. This is a very important problem from the exam point of view, so pay due attention in solving it. Exercise problem 2.31. How many electrons in an atom can have the following quantum numbers? You are given two sets of quantum numbers, n equal to 4, ms equal to minus half, and n is equal to 3, L is equal to 0. Now let us take the first case. We are given the values of the shell. Okay, now you are asked to calculate the number of electrons in an atom, okay, with n equal to 4. So here you are given the value of the shell n equal to 4. We have come across a formula for calculating the total number of electrons in a shell when you learnt about a principal quantum number. What is that? It is equal to 2n square. The number of electrons in a shell is given by 2n square. This is the formula. So in the first case, since you are asked to calculate the number of electrons in the fourth shell, you can apply this formula. Okay, so it becomes 2 into 4 square. So you get 32 electrons. And what is the next quantum number given in the first case? ms equal to minus half. Okay, so it means the spin orientation of the electrons. Okay, you are asked to find out the number of electrons with this spin orientation. See, I told you an orbital is occupied by 2 electrons. Among these 2 electrons, okay, each electron spins in the opposite direction. When one electron spins in the clockwise direction, the second electron spins in the anti-clockwise direction. So the value of ms for one electron in an orbital is plus half and the other electron in the same orbital is minus half. Since you got 32 electrons as the answer, okay, for the total number of electrons occupying the fourth shell, it means half of this population of electrons have plus half spin and the other half of the electrons occupying the fourth shell have minus half spin. So half the number of 32 electrons will have ms equal to minus half, which is equal to 16 electrons. So this is your answer for the first set of quantum numbers. So these many electrons having minus half spin occupy the fourth shell. Let's solve the second case. Here n equal to 3 and L equal to 0. How can you do that? Since n is equal to 3, it represents the third shell. L equal to 0 stands for a subshell. So it represents a 3s subshell or a 3s orbital in it. Okay, we know that each orbital is occupied only by 2 electrons. An s orbital can have only 2 electrons in it. So whatever be the number of n is equal to 3, n can be 4, n can be 5. Whatever be the value of n, the number of electrons occupying an s orbital would always be 2. So the number of electrons in this case, that is 3s orbital, is 2. I want you to do exercise problem 2.67 as your homework. How many subshells are associated with n equal to 4? So you are supposed to find out the possible values of L corresponding to fourth shell. What is the second question? How many electrons will be present in the subshells having a spin value of minus half for n equal to 4? Okay, calculate the number of electrons with the spin value ms equal to minus half which are present in the fourth shell. Do this problem as we did in the previous problem. Okay, so thank you for listening.